Okay. Hello, everyone. Thank you for coming for the second day of this QT workshop. Today, it is my pleasure to introduce the second invited speaker of this workshop, Alberto Amo. Alberto did his PhD in the Autonomous University of Madrid, and then did a postdoc at the Kastler-Brossel laboratory in Paris. And since 2010, he is a senior researcher at the Photonics and Nanostructures Laboratory, part of the CNRS and the University of Lille. So, Alberto, whenever you want.
Okay. Thank you very much. Can you hear me? Can you hear me well? Can you hear me well? Yes. Okay. Thank you, the organizers, for giving me the opportunity to be here and to introduce you to some of the concepts of related to the physics we are doing in our group and in many other groups, of course. So the idea of the material I prepared today is to give you an introduction to topology in general, in physics, and more in particular in topological photonics. So I will not review the results of our group in detail. I will show you some of them, but I will focus on giving you the notions of the basic notions on topology, very, very basic. So in 1.5 hours we cannot go very far. So that you go home with some tools to understand papers you read, to understand talks you hear to, and maybe some tools to go further and apply these concepts to your research. Okay? Maybe some of you are familiar already with topology, but just in case, I will just level from below. Okay? So please feel free to interrupt whenever you want, and we will make a pause at some point. Okay? Just as Carlos was mentioning, so I come from the CNRS and the University of Lille, and if you don't know where Lille is, it's right here. Okay, it's close to the border, to the edge. Edges are very important in this talk. So close to the edge, to the border with Belgium, and 1 hour away from Paris by high-speed train, and and this is a very nice city. It was part of the Spanish Empire for 150 years at the 16th century. So there are some remains of like architecture that was popular at the time, and it has this North Flemish look, very beautiful. Okay, so the notion of topology started in the 19th century. Okay, I'm going down to the 19th century. So these are one of the first works in which these notions were actually theoretized. This is a book from 1847. By this German mathematician, who described topology in the way you see here. Okay, so by topology we mean the doctrine of the modal features of objects or of the laws of connection important, relative position, and of succession of points, lines, surfaces, bodies, and their parts or aggregates in space. Always, and this is the most important part, always without regard to matters of measure or quantity. Okay, so the idea of topology is to describe an ensemble of things from a qualitative point of view. Okay, we don't want to know exactly what is the equation that describes this graph here. For instance, this is a line. It's a closed line. Okay, we could describe the line by just writing down the equation that tells you at which point in space the line is in this plane. Okay, but this is not the goal of topology. The goal of topology is to describe the properties of this line in a global way, no matter what is exactly the points of each part of the line. Okay. So just to give you an example of how this was thought in the very beginning, so we can take this line. This is a closed loop, just one loop. We can orient it, and this is something that mathematicians do when they orient it. So, well, the arrows are not very correct, but you can see there's some orientation in the line, so you can go through the line in this way, okay? And now what you see here, this number you see here, is what is called the linking number. So the linking number is the oriented number of times you cross the oriented line from a viewpoint. Okay, so for instance, let's go into this area here. Okay, let's select a viewpoint right there. Let's draw a line. Okay, and now we count the number of times we cross the line, and we put a sign related to the orientation of the arrow here. Okay, so here you cross the line twice, two lines with this orientation. This will give you +1, and then you have a 2, which is what's written here. Okay, so this 2 is actually an invariant. And it's an invariant because no matter how you draw this line, this perspective line, you will always find 2. Okay. So for instance, if I go this way, I will now cross 4 times this line. But in this case, I will have -1 because the orientation is the opposite, +1, +1, +1, and it will give me 2, okay? It doesn't matter. And it's very interesting because if you put your finger here, for instance, you put your finger here on the plane, and then you pull the rope, these 2 will be the number of times the rope goes around your finger, okay? For instance, if you put it here, where there is a 0, you put your finger there, and you pull the rope will go away without trapping you, okay? So these are the initial concepts that were then very much advanced by Poincaré at the end of the 19th century, who made a lot of things. Another popular way, and this I'm sure you have seen this in some talks, of describing topology is look at surface topology. Okay, so you can look at the surface. I try to find an invariant now. Okay, so we saw how we would define the invariant in this when we look at this this line, but we can now find an invariant on a surface. And one possible invariant is the genus that is defined here. So it's the integral of the curvature all over the surface. Okay, so this is the curvature at each point on the surface. Then you do this integral over the surface, 1 minus, and then you get the genus. And this number is an integer number, 0, 1, 2, 3, 4. And it counts actually the number of holes of the surface. Now you deform the surface, and this is what this German mathematician was telling us. It doesn't matter the numbers, the exact numbers, and the measures. Now you deform this surface, and then you have these other surfaces, and they all have genus 0. If you calculate this integral, it will give you the same number. Okay, and of course you have this very famous example. You take a donut, a torus, have 1 hole, so now the genus is 1, and all of these objects, all of these surfaces have the same genus. Okay, so this is very nice. This is from the mathematical point of view, and I can tell you there are still people working on today on topology very strongly. I have colleagues in a mathematician's lab close to mine in which they are working on defining invariants in very complicated spaces and dimensions, and it's still a very active field of research in mathematics. But how do we bring it to physics? Okay, so how do we bring it to physics? So of course this is somehow physical because it's a surface, but the way it has been used in the past 40 years, very popular way, is to look at band topology. Okay, so we look at a solid, for instance, this solid here. So this solid has 2 atoms per unit cell. Okay, it has 2 atoms per unit cell. And we look at the bands, the bands of eigenvalues of this solid. So the bands of eigenvalues, I hope you're familiar with a bit of solid-state physics, and you understand what's a band, momentum, energy, okay? So here you have 2 bands, okay? And we are going to look at the topology of the band. And I'm not referring to the topology of this surface you see here, which is just a torus. It's a torus, you see it very well because this is periodic in kx and ky. So this point here comes back to this point here comes back to this point here, and this makes a torus. Okay, this is a torus. It's a very trivial surface. I'm talking about the topology of the eigenvectors, okay, that are associated to this surface. So we can now look for an invariant, and one possible invariant is this one called the Chern number. And you see, it works on the eigenvectors of the surface. So I take one band, I calculate this integral here. So this is the gradient of this. Wave vectors in k, okay, multiply by this, rotational of the gradient, etc. I take the integral, and if I look at what is the result of the integral, it's an integer number again. Okay, so good, an integer number. We like it. We like it because it means that now if I deform the band, so I don't care too much about the form of these bands and how the eigenvectors are going to be deformed when I, for instance, when I compress the solid or when I pull it apart, this number will be preserved under certain conditions. Okay, so this is what we want. We want to look into these integer numbers, these invariants. Okay, and the first example into which this concept was very useful to understand what was going on in a system. I would say it was a very important example. It's a very important example. Is the quantum Hall effect. So I don't know if you're familiar with the quantum Hall effect. I'm going to explain it to you very basically. Okay, I think this version of the presentation is the one that is not going to work, Carlos. Okay, so at some point, because I see already that is the form. I don't understand what happened in between, but well, we'll see. Okay, no, let's keep it. Let's keep it. All right, let's keep it. Okay, so the quantum Hall effect. The quantum Hall effect appears in a two-dimensional electron gas. So imagine a sheet of electrons in two dimensions, and you apply an external magnetic field perpendicular to the sheet. Okay, and now you look at you apply a voltage, and you look at the resistivity of the material at the, longitudinal to the voltage and transverse to the voltage, and you see something very strange happening. Okay, and this is what these people found in 1980. You see that the transverse resistivity shows these plateaus here. Okay, so it shows these plateaus as a function of the magnetic field. So this is very strange, and the longitudinal resistivity is also even, I would say, even more spectacular, because you have some peaks at where the plateau is changing, and then the resistivity is 0. Okay, so the current is going through without any resistance. So this is just quite amazing. So how to understand that? Okay, so first of all, we see that the resistivity is quantized. Quantized in the sense that you see these plateaus. Okay, follow this rule, this law here: h over e squared 1 over n, and n is the number of the plateau. Okay, so it's a fundamental constant multiplied by a number. Okay, so this is telling us that there is something specific, something very universal, because it doesn't matter the shape of the whole bar. It doesn't matter the shape of your system. It doesn't matter if you have a little bit of disorder in your system. You will still have the same number. Okay, so it's very interesting. So what's going on here is the following: is that you have when you put a magnetic field, your two-dimensional electron gas should have parabolic dispersion. The electrons have a parabolic dispersion. They have a mass, parabolic dispersion in 2 dimensions. When you put the magnetic field, you have flat bands that appear. So this parabolic dispersion transforms into flat bands of levels, okay, separated by a gap. So now we have bands. In this case, they are flat, separated by a gap. Okay, so we started to see something similar to what I presented in the previous slide. And then these people, Taules and company, in 1982, very fascinated by this problem, what they did is to try to calculate the resistivity, not exactly in a two-dimensional electron gas, but in a two-dimensional electron gas in a lattice, in a square lattice. Okay, so a square lattice, and then putting electrons and looking at the resistivity, and they found that the resistivity was actually quantized. You see, e squared over h. Okay, multiplied by some integer. Okay, and this is the integer here, and you see that this integral is very similar to the integral I just showed you for the Chern number. So there are derivatives of the eigenvectors. These are the eigenvectors, derivatives over ky, kx, ky, and an integral over the whole real and so on. Okay, so it's very similar. Actually, this is the Chern number. This integral corresponds to the Chern number. Okay, so they found that by looking at the integral of the eigenvectors in the bulk, okay, they were understanding the resistivity of the system. And what's actually going on is that the conductance in this problem is not coming from the bulk; it's coming from the edges. This is already also a very interesting feature of topological systems. So you have now I put an edge. So these are my Landau levels, my flat bands. These are called Landau levels. And at the edge, they go up because I have a potential barrier here. So they need to go up, okay, in energy. And you see, if I set my magnetic field here, for instance, this means that I set a Fermi energy. So I just fill in this first level with electrons and a little bit of these guys, okay? And then here everything is empty. There are no electrons. So you see that I have a channel. I have a channel at the edge in which electrons go into the edge, and actually they can traverse through this channel on the edge. Okay, and from a semi-classical point of view, you see that in the bulk, you have the magnetic field is making close orbits for the electrons. They are just doing by Lorentz force. They are just going around like that. They are localized, but on the edges, these orbits are partially are half orbits. Okay, so you go here. You go here, you go here, you go here, you go here, and you can go around the edge. Okay, it doesn't matter the shape of the edge. You can see that the transport will happen anyway. Okay, so this is the robustness of this feature. And if, for instance, I now change the magnetic field, now I fill this other Landau level here. Now at the edge, I will have one channel plus another channel that was coming from the previous one. So then my conductivity actually will be twice, or my resistivity will be half. Okay, because I have two channels now. Okay, so this was the first application of topology, because this number I showed you is the topological invariant. And then Hatsuga in 1993 actually formulated in a formal way the connection between this bulk invariant and the number of edge states. Okay, so this is a very important notion. So the bulk invariant is going to tell me the number of edge states, of edge channels, that you can see in a very intuitive way in this view graph, that are related to the specific situation. Okay, so here I have charge number of 2. I have 2 edge states, and my conductivity is happens through 2 edge channels. Okay, very nice. So let me just summarize briefly the main ideas here. So the idea is to try to find in a solid an invariant, okay? And this invariant describes the bands of the solid, okay? So I have these 2 bands, for instance. In 2 dimensions, the invariant has this form, okay, this Chern number, and I can have a trivial solid, for instance, with a Chern number equal to 0, Chern number equal to 0, and I can have a non-trivial solid, a topological solid, with Chern numbers different from 0, okay? And now another way of seeing why an edge state should appear in your system is to look into this situation. So I have bands here with some geometry, some structure, some symmetries, okay, that result into a Chern number of 0. And here I have bands with a geometry, a structure that result into a Chern number of 1, for instance, or minus 1, doesn't matter. Okay, and you see that if I put the 2 solids together, if I connect them, I just paste them, okay, to go from this bands to these bands, something very strong needs to happen because the eigenvectors needs to rearrange. Okay, so the way they rearrange is in the following way: the gap closes. So here there's a gap. The gap closes. The 2 bands come together. Their eigenvectors rearrange, and the gap opens again. Now with a new structure that gives rise to a differential numbers. Okay, so that's why I should expect edge states at the interface, or interface states at the interface between two solids of different topology. Vacuum can be considered as a solid with infinite gap, okay, and with trivial bands. Okay? So Chern number equal to 0, and that's why in the quantum Hall effect, when we were putting the whole bar next to vacuum, we were seeing edge states appearing. Okay. Another important feature is that these edge states, in the end, they need to connect the 2 bands, okay? And when they connect the 2 bands, they have a group velocity, a well-defined group velocity, okay? And this well-defined group velocity makes these edge states chiral, so they go in one direction. You see, this is momentum, so this is the derivative of the energy with respect to the momentum is the group velocity, and you see they are going in one direction. So this means that for example, the quantum Hall effect, the electrons were going through the edge in one direction and without any backscattering. They were only going in one direction. And this direction, in that particular case, is set by the direction of the magnetic field. If I change the magnetic field, they will go in the other direction. Okay, very well. So what are the implications of this? And what are the implications for this for photonics? Because in electronics, I just showed you an example, but in photonics. So one very important implication is the following. And this can be applied to quantum systems also, of course. So imagine you have a photonic crystal. Okay, this is a photonic crystal. It's made of a triangular lattice of holes. So here you have photonic bands and a gap. Here is the same photonic crystal. And I just remove a line of holes here, okay? So I have 2 regions. In both regions, I have the same bands, okay? Separated by a gap, say photonic bands separated by a gap. And now this absence of holes makes a channel here. So I could send light here, and it should go through this channel. The problem is that if you do that, in principle it should work. I should have light going through this. But every time there is a corner here, there will be a strong backscattering. Very, very strong. That strong that if you fabricate this device here, at the output port, you will see almost no light coming out. Okay, everything will be backscattered. Now imagine you use not a regular photonic crystal, but a topological photonic crystal. Like for instance this one. So here I have 2 photonic crystals. They have different shapes here. You see, here it has small triangles. Here it has big triangles, okay? And it happens to be that in this particular example, these 2 photonic crystals have different topology. So they also have a gap band, photonic bands, a gap. And at the interface, because of this change of topology, actually there appears interface modes that go through this interface. And this interface mode, they just go straight, and there is no backscattering when you have a corner here. Okay? So this is a very important application for integrated photonics, okay? Integrated photonics technologies to know how to fabricate in a very easy way photonic circuits in a very small footprint, okay? Because now you can have very, very sharp corners here, and you can transmit light without any problem. Or another application, I don't know if I call it an application, but it's a demonstration that is very interesting, is to create a topological laser. So here you have a photonic crystal with some topology, and this topology actually comes from some external magnetic field applied to a magnetic material. And here you have another photonic crystal with with a different topology. And here they are implementing this group, the group of Boubacar-Kanté. They implemented the quantum Hall effect, basically, very similar to the quantum Hall effect for photonics. So now you have light that appears in this edge here, and it circulates in one direction. And they could see that it circulates in one direction, straightforward, no matter the shape of this photonic crystal, because they put a waveguide here, and they saw that the light coming out from the waveguide was going on only in this direction. And this was lasing. This was in the lasing regime, so there was a lot of light coming out of the device. Okay, so you can have you can implement a laser, integrated laser in a chip with a transmission only in one direction and robust to any disorder that in this region in which you lace. So these are just two examples. Yes. Yeah, so this so this photonic crystal, the way you do it is the following way. You just take this hexagonal unit cell, okay, which is made of triangles. You put the triangles in the center, and now you make a deformation in which you make triangles. You put them out away from the center or closer to the center, okay? So this is closer to the center. This is away from the center. So when the triangles are perfectly centered, there are two bands, but there is no gap. When you put them apart, there is a gap that appears, and when you put them closer together, there is a gap that appears. But these two gaps have different topology. So the bands that are associated to this have different topology, and that's what makes the channel. Okay. Well, it's of course much more subtle than that, but I don't want to go into the details because it's a bit complicated. But that's the idea. Okay, it's really the same idea. Okay, now. So this was like an appetizer of the main concepts, okay? And now what I would like to go over through this presentation is to give you a more profound example on 1D. So the SSH lattice, which I'm sure many of you already know, but for those who don't know, is the easiest introduction into topology, and we're going to calculate the invariant. Okay, we are going to explicitly calculate the invariant in this lattice, and we are going to see that depending on the value of the invariant, there will be edge states or not. Okay, so it's a one-dimensional example. Then I'm going to show you that we can create in artificial magnetic fields in photonic systems. Okay, so we will create a photonic lattice that shows properties for the photons that look like the properties of electrons under a magnetic field, even though there will be no magnetic field in the system. Okay, we're going to play some tricks to do that. And then if I have time, I don't know if I will have time because it's very difficult to calibrate a presentation of 90 minutes. If I have time, I will show you another kind of topology. Okay, so I showed you already what we call the Chern topology, with one of the quantum Hall effect. I will show you this SSH. I will show you this artificial magnetic field, and I want to show you another kind of topology which appears in systems that are driven in time, that are modulating in time, okay, and that give rise to edge states, even though the Chern number, so this bulk invariant, is equal to 0. Okay, if the Chern number is equal to 0 in a static system, there are no edge states, but in a dynamic system, in a driven system, there can be edge states, because there is another invariant that appears in the problem. Okay, so if I have time, I will go through that, and I will illustrate that with examples from results from our group. Okay, let's go. So, sorry if some of you are bored with this part, because this is very basic, and I'm sure some of you have already seen it. But let me go through it. So the idea is to give you an example of a system in which we can calculate easily the invariant, the topological invariant, and see the appearance of edge states. So the idea is to use be inspired by this molecule. This is an organic molecule, okay, that was studied by these people in this paper. This is a very seminal paper. Okay, so you see it's a carbon molecule, a one-dimensional chain of carbons in which there are some hydrogens, and then you have these two kind of bonds. You have a strong bond and a weak bond. Okay, and if you look at the electrons, the pz electrons of the orbitals that are actually coming out of the screen, those orbitals have electrons, okay, and they can hop from one carbon atom to the next. Okay, and you see when the bond is double, so the carbon atoms are a bit closer together, and the hopping is stronger. Electrons can hop stronger with higher probability than when it's simple. Okay, so let's try to describe this molecule in a very simple model, which is a tie binding model. Okay, so this is my view of the molecule now. So I have two types of carbon atoms, but they are the same. We linked with some strong link and a weak link. Okay, so now hopping of particles from here to here, okay, will be stronger than from here to here. So I can just write the Hamiltonian in the tie binding model like that. Okay, so you have T going from B to A, okay, or T prime going from n+1 to B. Okay, so this hopping here. Okay, and of course the complex conjugate and the whole lattice. Well, this is an infinite lattice, so I can just write this Hamiltonian in momentum space using the Bloch theorem. So then the Hamiltonian looks like that in momentum space. Okay, so it's in the basis of the A sides and of the B sides. Okay, so these are the A sides and these are the B sides. Okay, but all the A sides, all the B sides. Okay, in the Bloch vector representation. So I put zeros in the diagonal because the eigenenergies of the A sides I will put them to 0. The eigenenergies of the B sides I will put them to 0. And now these terms that you see here are the hoppings. Okay, so when I go from A to B, I have this term that appears here due to the hopping, this internal hopping, and also from A to B I can go like this way, or I can go also this way. Okay, and this way appears with this e to the ka. Okay, you're familiar with tie binding Hamiltonians. This is very simple. Okay, just wanted to make sure that you all understand. So now we can diagonalize this Hamiltonian and find the eigenvalues. Okay, so we have the eigenvalues. The eigenvalues are two bands. We have two atoms or two sides per unit cell, and you have two bands, and you have a gap in between. Okay, and this gap is actually T minus T prime. So it's the difference between the two hoppings. And there are two ways I can actually define the unit cell. I am free to define the unit cell in two ways. One way is I take the strong hopping here in the center of the unit cell, so T bigger than T prime. Or the other way is that I take the unit cell center around the weak hopping. The eigenvalues would be the same because the chain is exactly the same, so it cannot change. Okay, but the eigenvectors, because of this definition, they have a different form. Okay, and this is just a matter of the definition. So these are the eigenvectors. You see, plus is for the upper band, minus for the lower band. 1 over square root of 2. This is the amplitude on the A sides, on these sides, A, okay? And this is the amplitude on the B sides. And you see that they have amplitude equal to 1 in both cases, but there is a phase difference, a phase relation between the A and B sides. And this phase relation is actually given by this the equation that is below. You can see it there. And you see it depends on T and T prime, depends on the value of T and T prime. So in this case, I'm defining T as the hopping within the unit cell. Okay, so if T is bigger or smaller than T prime, this phase will have a different form. Okay, so what does it mean? It means that if we can try to define an invariant here, and the invariant in this one-dimensional case is called the Sag phase, or the winding number actually. Okay, and it's written there. So here, this is the invariant that we can define in this situation. So we can, this is we call it winding number, 1 over 2 pi, and you see it's always the same kind of form. It's the integral over the Brillouin zone of my eigenvectors with some gradient of k. Okay, so if we do it for the plus means the upper band. Okay, I do it only for the upper band. So here there is a plus. So I calculate this integral, and if I calculate this integral, I can see that. It gives a value of 0, okay, in this situation, when the T is bigger than T prime. And if I take T smaller than T prime, it doesn't give a value of 0, it gives a value of 1, okay? So, so as we will see now, this means that this dimerization is trivial and this dimerization is topological. Okay, if I have an infinite lattice, it doesn't make any difference, okay? But when it makes a difference is when I put an edge. So if I put an edge here, okay, I put an edge there, now I can really define my dimerization in a unique way. And the dimerization that is defined just by the fact that we need to have a unit cell that is well defined all over the lattice. So if I put the edge like that, so my unit cell will have a strong hopping, and if I put my edge in this situation, my unit cell will have a weak hopping. Okay, and then everything will be defined correctly. So let's see what happens with this. Okay. Of course, if t is equal to t prime, okay, you see that the gap is t minus t prime, so the gap closes. Okay. So you see that actually to go from the situation on the left to the situation on the right, I need to close the gap and then open it again. And when I open it again on the right, I have a topological phase. Okay, so this again goes with the notion of topological phase transitions, in which when you go from a topological phase to another topological phase, you need to close the gap and open it again. Okay, and you can see it here very clearly. Let's see if we can find like a more visual description of these topological invariants. Okay, so to do that, let's consider again our Hamiltonian. This is the Hamiltonian in momentum space, and I'm going to write it in this specific form. So this is a 2x2 matrix. Okay, I can do many things with 2x2 matrix, and what physicians love to do with 2x2 matrices is to put them in terms of Pauli matrices. Okay, we love Pauli matrices, and yesterday there was a lot of Pauli matrices already. There were a lot of Pauli matrices. So look, so we can write it like this. So I can write this Hamiltonian as a product of this vector multiplied by this vector of Pauli matrices. Okay, so sigma, this sigma, bold sigma, is a vector of the sigma x, sigma y, and sigma z Pauli matrices. So if I make this scalar product, I can write this in this way. Okay, so this sigma x is a 2x2 matrix, sigma y a 2x2 matrix, sigma z a 2x2 matrix, and this is a number. Okay, that depends on k. Okay, so you can see it here. Okay, so this dx, dy, dz vector, actually in this specific case, because sigma z is equal to 0, because there are no diagonal terms, it lies on the plane, dx, dy. Okay, and you can see what happens in two possible dimerizations. So this is what happens to the vector d when k goes from minus pi to pi. So it goes through minus pi over a to pi over a on the Brillouin zone. Okay, so this Hamiltonian. So the vector d in this case, if I put it on the origin, from the origin, it will just do something like that. Okay, okay. But in this situation, the vector d will actually make a whole turn around the origin. Okay, so it winds once in this case, and here it winds 0 times. It doesn't turn. It doesn't make any turn. Okay, so this gives you a graphical representation of the two different situations with the two different topological invariants. So this winding, and that's why this invariant is called winding. So this vector winds once in the topological phase, and this vector winds 0 times in the trivial phase. Okay. Well, let's now look at the finite size system. Okay, let's look at the finite size system. These are just results. So you take MATLAB or whatever, or Python, and you just diagonalize this chain for infinite size with a number of unit cells, and you look at the two situations. So I end my chain like that, or I end my chain like this. If I end it like this, I see some eigenvalues here that are arranged in two bands, and there is a gap in between. If I end it like that, in this situation, I see that there are eigenvalues, okay, in the two bands, and then I have two extra states right in the middle of the gap. Okay, and when I look at what's the shape of these states in real space, they are located in the edges. Okay, so here we have edges appearing in the system. So this is the eigenvalues in the bulk. Okay, those in the bands here. So you see that they are spread all over the lattice, while the eigenvalues in the edges are really in the middle of the gap are really on the edges. Okay, so this gives you it makes the link between the invariant and the appearance of edge states. So now let's try to see experimentally an implementation of this SSH lattice. So of course we could work with a real SSH lattice, so we could work with a real polyacetylene lattice, but it's very difficult to work with that because it's angstrom size. Okay, so you need to probe. Maybe it's possible with scanning with scanning electron microscopes and with tunnel microscopy or things like this. But one of the nice features about the photonic system is that you can implement, or atomic systems also, you can implement this kind of Hamiltonians very easily in your lab. Okay, because the sizes are very different. So the sizes are the typical sizes of light. The light is 1 micron. 1 micron is very easy to manipulate in a clean room. Okay, so this is the system we are going to use in the rest of the talk, actually, to visualize different effects and to study different effects. So and this is a system I'm working with for the past maybe 15 years. So the idea is to use these semiconductor microcavities. So they are made of 2 Bragg mirrors. As you can see here, this is a Bragg mirror, this is a Bragg mirror, and then there's a spacer in between. Okay, and and these microcavities have a Fabry-Perot mode. Okay, that confines light in the cavity. So at a very specific wavelength, you have light confined in the cavity. And what we do is that we put inside the cavity, we put also a quantum well, and this quantum well has electronic excitation that we call excitons, and these excitons actually mix with the light, and I will not go very much into the details, but it mixes with light and give rise to hybrid particles that we call polaritons that are partly exciton, partly photons. Okay, and because they have this hybrid nature, they have very interesting properties. Basically, they have, from the photonic part, we can visualize them because they escape out of the cavity in the form of photons. Okay, that we can detect with cameras and etc. We can also, I will show you how we can also confine light in the 3 dimensions of space because light is easy to confine. And then from the excitonic part, they have a matter part, so they have interactions, they are sensitive to magnetic fields, they can show, there's again medium for lasing, well, there are many other properties. I will not concentrate on this part here, on the matter part, I will only show results that come from the photonic part. So even if I put the quantum well away, all the results I'm going to show you will hold. So this is we fabricate this by molecular beam epitaxy. So in a 2-inch wafer here. So you have a 2-inch wafer in which you have a mirror, the cavity, and a mirror. And this is a few hundreds of nanometers in size. The whole structure is 10 microns in depth. So you do that, and now you can etch this 2-dimensional cavity into smaller structures. For instance, into these micropillars. So here is a micropillar. So basically, with e-beam lithography, you design a circle in the cavity with some resist. This is hardened, and then you attack the whole thing with ions, and the ions will destroy everything except for the region in which you have protected, down to a substrate. So they are not floating in air; they are on a substrate. These are like 9 micropillars that are separated there. Okay. So now light is confined in the 3 dimensions of space. So not only in the vertical direction by the Bragg mirrors, but also in the horizontal direction by the fact that these semiconductors have a very high index of contrast, of refraction, 3.5, and outside you have air or vacuum with index of 1, and this confines laterally the photons. So now you have like an artificial atom, a photonic atom, let's say. So you have confined modes. So this is the ground state. It's an S mode, it has an S shape, okay? It's 2-dimensional. So it has a Gaussian shape, 2-dimensional Gaussian shape. Then you have the P modes, so they have some lobes, and at higher energy you have D modes, F modes, etc. And this is going to be our building blocks. This is what's going to play the role of the p-set orbitals in the SSH that I showed you before. So we can couple 2 of them, so we can just fabricate 2 of them together just by designing the mask correctly. They overlap, and now photons can jump from one pillar to the other. Okay, and now we don't have any more like the left mode and the right mode. We have molecular modes. So for instance, the S modes, they give rise to 2 modes: the bonding mode, which is left plus right, and the anti-bonding mode, which is left minus right. Okay, and then we have more complicated modes if you start from the p states. So nice. This is our building block, and now we can fabricate 1-dimensional lattices. For instance, we can fabricate an SSH lattice. It's very simple now because we just need to put my 2 micropillars closer together, farther apart, closer, farther, closer, farther, closer, farther, and then we are staggering the hoppings of photons. And this is an experimental image. In the middle, you have an experimental image of the emission of light from this structure as a function of the angle of emission. And the angle of emission directly maps into the momentum of light in the lattice. Okay, by momentum conservation. So basically here what we do is we take a laser, we shine the structure with a laser at high energy. It creates electrons and holes in the semiconductor because all these, remember, are semiconductor structures. These electrons and holes relax down, they form these polaritons, or they populate the photonic bands, and then light is emitted. And it's emitted at the energy and momentum of the eigenmodes of the system. So you see in the lowest eigenmodes that come from the coupling of the S modes form 2 bands, a lower band, an upper band. Here you see less light because there are some interference effects. And then you have a gap in the middle. And this gap is the SSH gap that I showed you before. This is in real space. So in real space, you see light all over the lower band, the upper band, and the gap. Here are upper modes that come from the coupling of the P modes. Okay, so this is the SSH, an SSH system. And now we can try to look into the appearance of interface modes. Okay. By the way, I don't go into the details here, but we can measure the sag phase in this system. Okay, and we have done it. I didn't put a reference, but we have measured the sag phase that I showed you before by using some tricks that are available. And you can see that depending on how you select the unit cell, it gives a sag phase of with a winding of 1 or a winding of 0. But I don't want to show everything. So let's see the interface mode. So I told you we have two lattices of different topology at the interface. The gap needs to close and open again, so there should be an interface mode. So this is what we do here. We could do it at the edge. We could just cut the lattice at the edge, and we have done it. But I want to show you this example in which we take two chains. This is an SSH chain. Okay, you see the unit cell is the hopping in the unit cell is strong, weak, strong, weak, strong. And now I take another lattice here, in which I have a weak, strong, weak, strong, weak, strong. So if you remember correctly, this is the chain with winding number equal to 0, and this is the SSH chain with winding number equal to 1. If I connect them, and it doesn't matter how I connect them, if I connect them, to go from one situation to the other, the gap needs to close and open again, and there should be an edge mode, and this is what you see here. So this is the real space emission, okay, experimental. So you see the lower band on the right, on the left, on the right, the gap, and you see that in the middle of the gap, more or less in the middle of the gap, there is this interface state. Okay, and now you can look at it. I can select this energy of emission. So this is energy of emission. I can select that energy of emission and look at how it's arranged, and it has a maximum at this site, and then it decays exponentially on the left and on the right. Okay, and it has exactly the shape that you expect. Okay, so actually, we use this system in the same way I am using it today to learn about topology, and probably the way some of you already learned about topology using the system. So we use it to learn about topology. So we fabricated it in 2016-17 to learn about that, and then we also use it in a more original way, which is to make a laser. Okay, so we made a laser. We made the first laser in a topological mode that is published in this paper. So we lace in one mode like that at some point. If you pump correctly your system, so it shows you an exotic way of using topology in photonic systems, to make lasers in weird modes. Okay, so one more extra feature about topology is the robustness against disorder. Okay, this is a bit controversial nowadays, but in some conditions, actually, this topological mode, this interface mode, the interface mode I just showed you, is robust to some certain kinds of disorder, and it's disorder that preserves some symmetries. Okay, so you need to your system has some symmetry, and this symmetry is related to the appearance of this interface mode. As long as you respect the symmetry, if you put disorder, it doesn't matter how you put it, but if you respect the symmetry, your interface mode will not change. And this is what is shown in this view graph. So here we have the Hamiltonian, and this Hamiltonian has a specific symmetry, which is what we call chiral symmetry. Okay, chiral symmetry is defined like that. Okay, so if your Hamiltonian anti-commutes with any operator, this operator is called chiral symmetry. Okay, so in this case, sigma z is an operator that anti-commutes with H. So sigma z is our chiral symmetry. Okay, and it exists. It's equal to 0. Okay, so as long as if I put disorder now in my system, okay, and this is in K space, but I could write the Hamiltonian in real space, and I could also find a chiral symmetry. If I put any disorder that respects this situation, that respects the fact that H some operator is equal to 0, and the anticommuter is equal to 0, then it means that the spectrum has to be symmetric with respect to 0 energy. Okay, so I need to have the same number of modes located at the same energy with plus energy and with minus energy. Okay, so if I have a mode at 0 energy, and this H mode is actually at 0 energy, if I have one mode at 0 energy, okay, this mode is its own anti-energy mode. Okay, so so it means that if I have a mode at 0 energy, if I put disorder, this mode will not change in energy, because it cannot. It doesn't have a partner at opposite energy that will move in a symmetric way. So it will stay at 0 energy. And this is what shows this simulation. In this simulation, we have the two bands. These are actually the eigenmodes of a band. You cannot see it here because the band is very flat, but you have two bands and you have the topological mode. And now we increase disorder. We put disorder, random disorder in the hoppings, okay? In the hoppings. And if we put random disorder in the hoppings, we don't put anything on the diagonal of the Hamiltonian. And if we put, and this means that the chiral symmetry is always preserved. And then you see that the bands have a lot of noise now when we put the disorder. There is in the bands there is localization, Anderson type localization, etc. But the topological mode doesn't move a single microelectron volt. It stays there at zero energy. Okay, so the energy of this mode is robust to disorder, to this kind of disorder that respects this chiral symmetry. Okay, I just wanted to make this point because usually topology is associated to some robustness, and you need to refine very well what kind of robustness and what kind of to what kind of disorder you are robust to. Okay, and in this case it is this one. Okay, so just before we stop, two applications to quantum optics, just to make the link with a bit more quantum stuff. So this kind of SSH modes have been used to show a robust transport of quantum photons, in this case a biphoton state. Okay, so this is a chip, a silicon chip in which there is a lattice here, and this lattice is the SSH lattice, and then you have an interface mode like the one I just showed you, and then if you propagate photons in some quantum state, this quantum state is particularly preserved because you have this robustness that I just told you about. This is another example, actually, from people here from ISM, the Institute of Ciencias de Materiales, okay, in which you have an SSH or similar chains, and then you can now create have an edge mode here, an edge mode there, and you can use interfaces between different kinds of topological SSH chains, or this is not an SSH, but it's very similar. You can make these interfaces to actually create modes that overlap, and now you can transfer your quantum state from this side to this side thanks to this overlap of these edge modes that appears because you have these interfaces not far apart. So you can arrange this lattice in a way and use some protocols to transfer a quantum state from the left to the right in a very efficient way. Okay, and robust to certain types of disorder of the lattice. Okay, so these are just two examples. There are many more. So maybe we can stop here now for 5 minutes, and then I will make a shorter second part. Or yes.
Okay, so maybe are there any questions before the break? Yeah.
So my question is related to dissipation. So what do you do when, I mean, because if I understood well, for the SSH model is at least for the electronic Hamiltonian is a single electron Hg spectrum. So I don't know if your case is a single photon Hg spectrum, or you have, since it's a linear system, or what happens with dissipation essentially.
Okay. So you here, well, photonic systems have dissipation. So you can see dissipation you can consider dissipation into different ways. You can consider it as a problem or as a no problem. So basically you have here, what are the energy scales of the system? So the energy scales of the system are, in this case, are the hoppings, okay? So in the electronic systems, the energy scale of the system is the hopping, okay? There is no other energy scale. And in photonic system, you have a second energy scale, which is the dissipation that you showed. So if the dissipation is smaller than the other energy scales, the hopping, for instance, you can use the concepts related to the Hamiltonians that I showed you. The Hamiltonians I showed you are all conservative, of course. There is no dissipation in those Hamiltonians. And those Hamiltonians allow me to predict very well these bands, this edge mode, the shape of the edge mode, the shape of the band, of the eigenvectors, etc. I can predict them very well, as long as the dissipation is smaller than the hopping. So you see here this a line width, okay? And this line width is there and is related to this dissipation. There's another way of thinking of dissipation, which is to use it as a resource. Okay, so actually, all I'm going to present you today is standard conservative topology, even though we use it in a dissipative system. But in this context, in which the dissipation is smaller than the other energy scales of the system, but there is a whole branch of topology, and particularly of topological photonics, in which you define, you play with the dissipation, and the dissipation gives rise to the manipulation of the dissipation and the structure of the dissipation in space, for instance, give rise to new topological phases and new topological invariants. And you can define topological invariants in which the dissipation plays a central role. I mean, so this is what is called the non-Hermitian topology, and it's a whole branch of topology that is very popular for the past 6-7 years. I will not talk about that.
Okay. Is there any other question?
I just wanted to ask, why is the energy of the topological mode closer to the upper band than to the lower?
Yes, so it should be at zero energy. Okay, this is what appears in this you do these calculations. It should be at zero energy, or what appears here should be at zero energy. So this is because in these systems, this tie-binding Hamiltonian is a two-mode model. So you have side A, side B, and the hoppings, and that's it. But in reality, in our photonic system, you don't only have the S modes. Okay, these pillars have also P modes. Okay, these P modes actually couple to the S modes and deform the bands. Okay, and you see here that the bands you see here, this band is narrower than this band here, and this is because there is some coupling of this molecular mode to the P modes. So it's a deviation of the tie binding approximation, and this also changed the energy of the H mode.
Okay. Any last question before the break? Okay.
About the experiment, I think I missed it. But what's the wavelength of this system?
Yes. So sorry, I just put all these details under the carpet. So you can see here it's 1.4 electron volts. So this is around 800 nanometers. Okay. All these semiconductors, they have gaps that emit at around 800 nanometers. So all this happens at those wavelengths.
And then you have it in a code?
Yes. So all I'm showing you here is purely photonic. I don't need the quantum wells for anything. It's just that the system we traditionally use has this quantum well, so we use it with a quantum well. Okay. For this, so it's designed to work with the quantum wells, and the quantum wells, to have these electronic excitations working, they need to be cold at 4 Kelvin, because the binding energy of the exciton is 10 millielectron volts, so it needs to be below room temperature. So then we design the whole structure for 4 Kelvin, okay? Because the indices of refraction actually change with temperature. So because all this is designed to work at 4 Kelvin, even though we don't use here the excitons, all these experiments are at 4 Kelvin. We could design a microcavity that works at room temperature without excitons, and we could see the same things.
Okay, thanks.
Okay, so now maybe we can start this 5 minutes. It was okay, 5 minutes break. Okay, thank you.
Genial. Pues I'm not going to show you everything because I don't have time. But I think it was nice to go slowly. So that you grasp some basic concepts of this field. So this is a very famous diagram table, which classifies solids or systems. Let's say systems, depending according to some symmetries. Okay, and it tells you if you have these symmetries or you don't have them actually. If your system will show up a topological invariant or not. Okay, so so this here I show you this table. So it classifies the systems according to 3 symmetries. Okay, so this is time reversal symmetry, this is particle hole symmetry, and this is chiral symmetry. Okay, which I just defined. So it tells you if you have or you don't have these symmetries, if there is any chance that you will find, well, if you will find a topological invariant, that it will not be trivial or not. So for instance, the quantum Hall effect that I showed you in the beginning. So the 2-dimensional electron gas subject to a magnetic field. So it doesn't have time reversal symmetry. So if there's a 0 there, because you're putting a magnetic field, it doesn't have particle hole symmetry. It doesn't have any symmetry actually. Okay. So because you don't have any of these symmetries, you can actually define a topological invariant in 2 dimensions. Okay. And this topological invariant is the Chern number that I showed you. These guys have also another paper in which they have the same table, but extended to like up to 12 dimensions. Okay, so you can see, for instance, the quantum Hall effect. There is no quantum Hall effect in 3 dimensions, but there is quantum Hall effect in 4, 6, 8, etc. Okay. The SSH model that I just showed you is right here. So it's a bit boring because it has all the symmetries. So you see, it has time reversal symmetry with a +1, and with a +1, there is a +1 because we are using bosons. Okay, so T square. So this time reversal symmetry operator square for bosons is 1. Okay, so so it has time reversal symmetry. It has particle Hall symmetry. So the upper band and lower band are symmetric. And it also has chiral symmetry, okay? And then it tells you, I mean, this table, that these guys worked out, tells you that there should be an invariant in 1 dimension, which is the one I showed you, the winding number, okay? Then there are these other two, for instance, here, this class here, A2, in which time reversal symmetry is present, but for fermions, for electrons. So T square is equal to -1, this operator is equal to -1. And in this case, you have these other invariants. They are not the same as these ones. They are not Chern numbers. They are another type. This Z2 invariants, okay, and this class of systems is what we call this quantum spin Hall effect, or topological insulators. Okay? Topological insulators fall into this class. So these topological insulators, they have also edge modes, but they have edge modes for spin up going in one direction and edge modes for spin down going in the other direction. Okay, and they are these topological edge modes are actually protected by this time reversal symmetry here. So and there are many others that have been explored. For instance, this class has also been demonstrated experimentally, okay, in photonics, and maybe others also. Yes, of course, all these classes here are belong to superconductors, okay, are topological classes in superconductors, and some of them have been also explored and observed experimentally. Okay, so you see, for instance, to observe the quantum Hall effect, you need to break time reversal symmetry. And this is a problem in photonics, because to implement this kind of topology, you need to break time reversal symmetry, and in photonics it's not very easy. This one does not break time reversal symmetry, okay? It preserves time reversal symmetry, but you have the -1 here, okay? So you want to, which is something you have with fermions, but you don't have with photons. So you want to do it with photons, then you need to break some tricks to try to make some kind of like time reversal symmetric operator that looks like this. And there are tricks to do it. Basically by mixing time reversal symmetry with crystal symmetries, and then when you have some crystal symmetries, you can actually implement this kind of operator. So what I'm going to show you now, what I would like to show you now, and it will be the end, is how, related to topology, but it's not strictly topology, is how to engineer artificial magnetic fields with these photonic systems. Okay. So remember, a magnetic field in a two-dimensional system was giving me the quantum Hall effect. So I'm going to have something similar, not the quantum Hall effect, but something similar, when using artificial magnetic fields. So my goal here will be to show you that we can construct Landau levels in a photonic system, okay, without an external magnetic field. So Landau levels, you remember, are the flat eigenmodes of the of the two-dimensional electron gas under a magnetic field. So to do that, we will use a trick that was developed by these people here, Kinea, Katznelson, and Game, which is to use strain in a lattice. So now we are not going to use a two-dimensional electron gas. We're going to use a graphene sheet. Okay, a graphene sheet can be seen as a two-dimensional electron gas. It's just that it doesn't have a parabolic dispersion. It has a Dirac dispersion. Okay, but it's a two-dimensional system. So what they found, these people found, is that if you take a graphene and you strain it in the right way, you can actually engineer an artificial magnetic field. So there is no magnetic field, but you will still see Landau levels. And some previous work has been done in photonics by the group of Moti Segev and Michael Drexman in 2013, okay, in which they saw some localization of light that they ascribed to the presence of these Landau levels. So let's see how it works. I will base the description of this phenomenon in our lattices. So you see here, now it's not a one-dimensional lattice, it's a two-dimensional lattice of micropillars. It's an hexagonal lattice, so this mimics graphene. So here I have the micropillars, okay? Somewhere here is the upper mirror, the lower mirror, in the middle the cavity, and then you can jump from one micropillar to the next, okay? And it makes this this lattice. So if you look at the modes of a micropillar, the S modes, they look like the PZ orbitals of carbon in graphene. They are cylindrically symmetric, and now the photons can jump from one carbon atom from one side to the next, okay, like electrons in graphene. So if I look at the dispersion of the dispersion of modes, so the bands of this structure here, I see this. This is momentum, okay, which is the angle of emission of light, but I convert it into implant momentum, and this is energy, so this is the wavelength of light. So you see that I have the lower bands, which come from the coupling of these S modes, and you see there are two bands, and if you look carefully here, there is a Dirac cone, exactly like what you would expect from graphene, because the Hamiltonian is really the same. You can also look into the P bands, so the coupling of these P modes that are up here in energy, they also couple, and because they have now we have two modes per site, and I have two sites per unit cell, so I have 4 modes per unit cell. So it needs to give 4 bands, and this is what you have here. You have 4 bands. So you have a flat band here, you have some pseudo-flat band here, and you have Dirac cones here. Okay, so these Dirac cones have a very similar nature to the Dirac cones here. Okay, nice. So now let's try to see if we see how this magnetic field appears. So following the work of Game and co-workers, Grates Salerno and Jacopo Carusotto, they just worked out the problem for photonics, and what they did is the following, or basically what you can do is the following. You take your Hamiltonian, okay, and you linearize it around the Dirac cones. You linearize it around the Dirac cones, and the Hamiltonian linearized around the Dirac cones looks like this. So this Q is the momentum around the Dirac cones, okay? So now I'm sitting here, okay? This is my origin of momentum. So I have a Dirac cone in 2 dimensions. So this is how it looks. So it's a 2 by 2 Hamiltonian because I have 2 sides. Remember, I have the blue sides and the red sides. I have two sides. So this is my basis. And these 2 sides, when you can repeat the whole lattice by using these 2 sides. So I have this 2 by 2 Hamiltonian, and now this off-diagonal terms, okay, I can write them in this way. So I can just force myself to write it in this way. It's possible. So you can. It's a possibility. It's a way of possible way of writing it. So you have this dispersion here. So this is Qx, okay, Qy. So these are the wave vectors, and then you have the Dirac velocity in x and y, which should be the same, okay. You have and then you have this extra term here, okay, this extra term here. And if you look at this this form here, this looks like the form of a charged particle. I mean, the Hamiltonian of a charged particle in a vector potential. Okay, so A is a vector potential. There is no square here, okay, because this dispersion is linear. But if you had massive particles and you write an electron in a massive electron under a magnetic field or an electric field in a vector potential form, in the minimal coupling form, you will have an expression that looks exactly like this. So what is the form of this pseudo vector potential here? So it's written here, okay? So you see it is related to the hoppings, T2, T3, T1, T2, T3, okay? These are the hoppings here of the lattice. So if all my hoppings are the same, T1, T2, T1, T3, all the same, like in regular graphene, these vector potentials are all 0. Okay, and then they are all 0, and then I have a very simple expression of these terms. So it's just the Dirac velocity multiplied by Q, which is what you would expect for graphene. And this is what happens in regular graphene. But now you can see that if I manipulate the hoppings, I can make these vector potentials different from 0. And this is what happens. So for instance, I'm considering the case in which T2 equal to T3. Okay, so AX will be 0. But T1 will be different from T2 and T3. Okay, so now AY will be different from 0. So I can have a vector potential. And now if I want to have a magnetic field, I need the gradient of the vector potential to be different from 0. So this is what we do. We do the hopping T1 spatially dependent. Okay, so you see here the hopping, these distances are different in different positions. So there is a gradient in the hopping of T1. Okay, so then this gives rise to a vector potential with a gradient. If you calculate the gradient, it gives you the magnetic field, and then you have a non-zero magnetic field here. Okay? How is it possible that I have a magnetic field if I'm not breaking the reversal symmetry? Okay. The reason is that in this expression here, you have this term here, which is called the Weyl term. Okay, and this has 2 values, +1 and -1. Okay, +1 for one of the Dirac cones. Okay, remember I have 2 Dirac cones. Okay, so +1 for one of the Dirac cones and -1 for the other Dirac cone. So actually the total magnetic field of the system is 0. This is correct. We are not putting an external magnetic field. But locally, if I focus myself on one of the Dirac cones, I have a local magnetic field that is different from 0. Okay, I will be opposite on the other one. But this is good enough to for instance to see Landau levels, because Landau levels in my two-dimensional system are separated by some energy. Okay, and the separation is the same whether the magnetic field is positive or negative. As long as the magnetic field has the same value, the separation will be the same. So I can use this to engineer Landau levels, and this is what happens here. So this is a tie binding simulation in which we are using this gradient in the hoppings, and you see that now the Dirac cones are not conical anymore. Now they have this structure. So you have a 0 Landau level here, okay? Then you have a n equal plus 1, 2, 3, etc., and minus 1, minus 2, minus 3, etc. Okay, so you have Landau levels that appear. They are not completely flat because we have this gradient of the hopping. Okay, if I make my system very, very far, very, very big, and the gradient is very small, these levels will be almost flat. So let's try to see this in experiments. Okay, so this is my my regular graphene, photonic graphene. Okay, so I have the two bands, the Dirac cones, and I without any strain, and I look at the energy of emission of the Dirac cone in real space. It looks like that. So I have maxima of emission at each micropillar. Okay, hexagonal, very nice. That's what we expect. Now let's put the strain. Okay, when we put the strain, everything becomes more complicated. Okay, so we have put the strain, and now I have my two bands become many bands. Okay, and if you look at the close to the zero energy, you see that the nature of the emission is very different. So here I have light coming from all the sides. Here I have light coming only from the B sides. Okay, only from the B. Okay, only from the B sides, and not light coming from the A sides. And this is a feature of the n equals 0 Landau level, and I will explain you that in a second. Here you cannot see very well the things because these S modes, the line width is actually quite big, and the magnetic field that we implement is not big enough. But we can go into the P mode. Okay, remember they have these P bands, and in the P bands, I have flat bands on the top and the bottom, but in the middle I have these Dirac cones. The nice thing about the P bands is that the hopping is stronger. Okay, and then this energy span of the bands is much bigger. So then I can see things easier. So again, I look at the energy of the zero. This is without strain. I look at the energy of the Dirac cones, and my emission looks like homogeneous, hexagonal homogeneous on all the pillars. Well, you see that there are some lobes here. There are some lobes. I don't know if you can see them, but there are some little lobes inside the micropillars, and this is because the structure of the P modes have these lobes. Okay. Now, let's put the strain. Okay. Again, it becomes very complicated, but if we zoom in carefully, so this is the zero energy. Okay. If we zoom in carefully, you see that there is this mode here, this mode, and this which corresponds to the 0 Landau level mode. Okay. And below, we have the n equal minus 1 Landau level, and the n equal plus 1 Landau level. We don't see it very well, but it should be up there. Okay. And if we look in real space at the energy of the n equals 0 Landau level here, okay, we see again this asymmetry. So we have light only on the B sides. Okay, B, the red ones. The red ones are the B sides. We have light only on the B sides. Okay. So this is actually what you would expect from the n equals 0 Landau level. Using that has been created with an artificial magnetic field. With a real magnetic field, if you go into graphene and you put a real magnetic field, what you would see is that in both cones you will have the same magnetic field. Okay, in one Dirac cone, you look at the eigenfunctions of the n equals 0 Landau level, you would have light or particles located in one sublattice. Okay, on one sublattice, the A sublattice, for instance. On the other Dirac cone, you have the same magnetic field. You would have your eigenfunctions will be localized on the B sublattice, okay, on the other one, okay. So overall, when you look at the system, you have particles in the n equals 0 Landau level under a real magnetic field located on both sublattices. Here we have this magnetic field on this Dirac cone, so on the B sublattice, okay. And here I should have on the A sublattice, but because my magnetic field is opposite, it's actually also on the B sublattice, okay. So in both Dirac cones, I have my particles, my eigenfunctions localized on the B sublattice because I have this opposite magnetic field. So, and this is what we see here. Okay. This is what we see. And why the B sublattice versus the A sublattice? Well, this depends on the gradient of your strain. If I change the sign of the gradient, then everything will be localized in the A sublattice. Okay, so this is a nice feature that so we can create these Landau levels, so the n equals 0, but also the n equal 1, and it's a nice way of creating flat bands in your system. Okay, a high density of states in a photonic system. But we can see more than that. You see that here in this time-binding simulation, you have the n equals 0 Landau level, and then you have some modes that go up and go down. Okay, so these are edge modes, and these edge modes remind the edge modes that I showed you in the quantum Hall effect. Okay, but they have a difference. The difference in this case that we have this artificial magnetic field with opposite signs in different Dirac cones is that the edge modes are all localized on the same edge. Okay, in the quantum Hall effect, I had a mode going that way in that edge, and a mode going the opposite direction in the opposite edge. Here you see the color is the edge, so they are all the edge modes are located on the right edge, even those corresponding to the old Dirac cone. They are located on the right edge, and we can see them here. You can see there is a line going from the n equals 0 Landau level down. Okay, there is a line connecting this. You make a careful analysis. There is a line connecting these modes here, and this line corresponds to these edge modes. So let's look at the edge modes. Okay, this is what I just explained. So look, we can look at the edge modes physically within our system. We can just take our lattice. We can pump on the right edge. On the right edge, we should not see any edge mode. Okay, so we see some propagation because we are populating also bulk modes. We see some decay of the wave function, but when we pump the system, we excite the system on the other edge, we see that there is there are these two lines going up and down. Okay, and this corresponds to the edge modes. Again, a difference here is that they are all located on one edge, and they go in both directions. So in the quantum Hall effect, it will go only in one direction, but here they go in both directions because we have opposite magnetic fields in opposite Dirac cones. Here in the lower pictures, you can see clearer the presence of edge states. So this is the momentum space when exciting the right edge, and you can see this line connecting the n equals 0 and n equal -1 Landau level. And on the left edge, you can see that there is a gap between the two because there are no edge modes in that region. Okay, so I think I will not show you this. Okay, so this is something else. It's in a different system. But I can just mention, maybe I will just give you the introduction of this part, and I will not show you any of the results. But there is in 2013 actually. So all these topological modes that I showed you are known from some time ago. So the quantum Hall effect from the 80s. In 2005, it was discovered a new topological phase, topological insulators, which were these Z2 phases that I showed you in the classification of symmetries. And in 2012-13, there was another topological phase that was discovered, and it's a topological phase that appears when you drive periodically in time your system. Okay, so it's based on the fact that when you drive periodically in time your Hamiltonian, you not only have a periodicity in momentum space in kx, ky, you have a lattice. Okay, you also have periodicity in energy, in quasi-energy. Okay, so basically you have your Hamiltonian that looks like this. Okay, it's periodic in space, it's periodic in time, and now you can apply also similar to the Bloch theorem in space. You can apply what we call the Floquet theorem in time. Okay, so your eigenfunctions, they look like this. They have this quasi-momentum that is defined here, but they also have this quasi-energy that is defined here, and it's defined modulo 2 pi, like the quasi-momentum is defined modulo 2 pi. This means that if you have a lattice system with two atoms per unit cell, you have two bands. And if you look at the Brillouin zone looks like this. Okay, so it's periodic in K, but it will also be periodic in energy. Okay, so this is the upper part of the Brillouin zone, and this part actually connects to the lower part. So this is well known from Floquet physics, but it has many implications for topology, because now you can have this kind of situation. You can have this band in which these two bands, which have some Chern number, for instance, +1, -1. So they are connected by an edge state at the edges. Okay. Now you have this gap, and look what I can do now. I can just modify my system such that the upper gap is closed. Okay. You can see it here. The upper gap is closed. Okay. And open again. and I can open it again. And I can open it again in a different topological phase. Okay? So the edge state in the middle has not disappeared, but I am in a new topological phase. And in this new topological phase, it can have this shape that I'm showing you here. So Chern numbers now become 0. After this topological phase transition, Chern numbers become 0. The two bands actually touch, but they touch through this gap. And when they open again, there are new edges that appear and that traverse that are on both gaps. So here you have a situation in which you have a two-band system with 0 Chern numbers, but edge states all over the gaps. And the reason is that there is a new topological invariant that you can define, and that is related to the motion in time of your system, how you move it in time. And it has this shape. We call it the Rudner invariant because it was discussed by Rudner in 2013 in this paper. And you see, it's again derivatives in kx, ky, derivatives in kx, ky. But here now you have derivative in time. Okay, you have a derivative in time, and the integral is also in time over the Fouquet period. Okay, and then you can have this new winding number. So now you see here that in this situation you have a winding number of 1 in the middle gap. So these winding numbers are actually defining the gaps. A winding number in the gap, and here now you have a winding number in this gap and a different and a winding number of 1 also in that gap. Okay. So I will not go into details of this, just to show you that there are many different topological phases, and we have implemented these topological phases using a different system in which some fiber loops in which light circulates in the fiber loop, and we can modulate the Hamiltonian. We can engineer a Hamiltonian that we can modulate in time. Okay? And I will not go into that, but even though the results are very beautiful, in particular, we can measure the Chern numbers in this system. This is the Berry curvature for the specialist. So we have the measured Berry curvature of this system. So these are the two bands. These are the Berry curvature. You see that there are points of high Berry curvature at this point and at this point, but the overall Berry curvature is equal to 0. So the overall Chern number is equal to 0. And then we can also see the anomalous phases experimentally, in which you have bands with 0 Chern number and edge states that traverse the bands, traverse the gaps, both gaps, and we can observe that experimentally. Okay, so let me just summarize. So if you want to, keep some very simple messages to bring home. So topology, bulk invariance, and bulk edge correspondence. Okay, this is the main ingredients. So you are always trying to look into the invariance and the associated edge states. It's a great tool to route photons in a chip. For instance, we are now using it in my lab to fabricate devices, terahertz devices. So we are fabricating terahertz photonic crystals using this concept, so that we can squeeze everything into a small chip. Okay, and then we are trying to do some functionalities with that. And there's almost everything to be explored in the quantum regime. There are very few experiments using, at least in photonics, using topology and quantum regime. And I wanted to advertise some future perspectives in our group. So we are trying to set up, we are fabricating a new, actually to go into the quantum regime, we are fabricating a new device, a new setup, in which we are fabricating a cavity, but this time it's not a monolithic cavity like the one I showed. It's an open cavity. So it's 1 meter, 1 meter, and then we bring them together with piezo actuators. And we want to put some molecules here, DVT molecules. These are quantum emitters. And we are planning to put these quantum emitters here and study the interaction of these quantum emitters with the photonic modes of this lattice that we are fabricating. Okay, and we are looking for PhD students to do that. So if you are interested or you have friends who might be interested, please spread the word. We are looking for PhD students. Okay, so this is the people who participated in this. I showed you a lot of results from our group. So this is the people from FLAM, collaborators from C2N, where the samples were fabricated, theory collaborators also from here in Madrid. And with this, I thank you for your attention.
Thank you very much, Alberto, for this great talk. Since we are a bit short of time, maybe we have time for a single question. Okay.
Maybe this is a basic question, but how do you measure in momentum space?
Yes, so we look at the angle of emission of light from the structure. So we have a two-dimensional structure, or the planar cavity or the lattice. So light is emitted in different angles, okay? So we look at the angle of emission at a given energy. So Basically, physically how we do it is we put a lens. So this is my lattice. I put a lens here. If I put a second lens, I make an image of the surface of the lattice. Okay. But if I put a third lens at the focal plane of the first lens, this is well-known optical physics. I mean, very well-known. I can make the Fourier transform actually of my real space emission. So it means that the image that I will have here is an image of the angles of emission of light. Okay, and this angle of emission, because of momentum conservation, so I have photons that are doing this. Okay, so when they escape, they have a momentum in the z direction and a momentum in plane, and the momentum in plane is the momentum that they had inside the cavity. So angles of emission correspond to momenta inside the cavity. So it's very simple experimentally.
Okay, thank you very much. Well, of course, you can further discuss in the coffee break. So we can go to the place we were yesterday, and let's thank Alberto again.
Thank you.